So, respected Mr. Pranab Das, sir, and dear student, on behalf of School CSIT, on behalf of Jain University and Mile Education, I welcome you all in this innovative learning industry connect session. So, I just want to introduce today's guest, Mr. Pranab Das. Is a digital innovative dynamic leader and a strategic planner. He has near 22-year experience in the information technology field. He has completed his BTech in electrical engineering from the University of Kolkata, and after that he has completed a master degree from IIM Ahmedabad. In his career, he has worked with various companies like Infosys, Walmart, Tesco, Reliance Industry as a project manager, and also work as a vice president with the Reliance Industry Limited. He's now currently he's also worked with as a head of IoT and smart production devices with the digital era company Alexis. Currently, he is working with smart AIoT IIoT products and sustainable future of water. Now I call Mr. Pranab Das to share their experience with our students so they can have number of things with them. Thank you very much. Pranab sir.
Yeah, thanks, Deepak. Hi, everyone. Let me first share my screen. Means you're able to view my screen, right?
Yes sir, yes sir.
And are you able to see what I'm writing on the screen?
Yes sir, yes sir.
Okay, yeah. Thanks, everyone. Okay, I have already taken a couple of sessions with you, so I will not spend too much time on introductions because Deepak has already introduced me, and thanks for that. Uh, so, Taking into cognizance this particular audience for you guys, kind of who are in kind of AI and ML at different semesters, most of you in due course, after some time, you'll basically get into the industry. So there is a specific difference between the academia and the industry when it comes to kind of AI and ML and deep learning and data science and all of these. While academia is there to kind of develop all of these concepts and models and algorithms, we in the industry are primarily invested in application of those particular models and kind of algorithms which comes across. Now, however, it's not really like a one-to-one kind of transfer of knowledge from the academia to the industry, in the sense that you'll see like normally even when I was in college and everything, like we used to go to the Kaggle and kind of get a data sheet, kind of what do you say, data extract and basically apply the models on top of that. However, you will see it's not in Kaggle you get it in a perfect format, so you can just take it and apply a model, and that's how it is. Here you will see, I think, uh, uh, applying a model, developing a model, and applying a particular machine learning model on top of it to derive a particular inference is something which comes at the very end. There's a lot of effort which goes in order to kind of identify the scenario, identify the use case. I mean, how to kind of model that data, get the data into a particular structure, how to pre-process that data, and then even finding out what's the appropriate model to be applied on top of that, which will kind of apply to the specific use case. So in this particular case, also today we will kind of look at a real life use case which we have used. And just to be very frank, I have worked mostly in the retail and telecom background. Manufacturing is new to me. So this is the first time I'm in a kind of a manufacturing domain. So kind of you will see this particular use case when we'll get into detail of that is very different, and any standard use case or a model doesn't necessarily apply to it. So without any further ado, let's see what that model is all about, what the use case is all about first. And from the use case, we'll get further into how we went about kind of solving it. The idea is that this is not a completed scenario. We are still working on that. So one of the reason why we bring it to you is that to kind of know your suggestions, and you know where to find me in LinkedIn. If you want to kind of get back to me with your suggestions, questions, you are most welcome. So now here is the context. I think as Deepak was mentioning, we work in the water and energy space, water and energy, and we are predominantly a manufacturer. However, the particular division that I am kind of heading, it's basically into kind of creating AIoT products, which is kind of artificially intelligent Internet of Things kind of products as such. And the other part that we look into is basically smart products, which is like we have products, and then how do we make the products much more smarter? So here, the particular diagram that you see out here is typically something which is called this is one pipe, this is one pipe, and this is another pipe, pipe number one and pipe number two. If we need to join these pipes, the entire water network, the water infrastructure practically is dependent on that. Like it runs for kind of thousands and thousands of kilometers to kind of bring the water from the source to the locality, uh, so that it kind of reaches us to your taps. So in that particular context, you will need to join pipes. Now, I mean, this is not the pipes that we see in our bathrooms and stuff like that. It is kind of pipes of much higher dimensions. So it's important that when we join those pipes, that join which we call the weld. So this when we weld two pipes, so that welding needs to be perfect. If it is not, obviously, as you can understand, there is going to be leakage and water is going to kind of go off that, and it's a huge exercise. I will show you a video to see, like it's not like one or two person's effort. It's kind of a lot of people come together to kind of do those huge joints in the water infrastructure network. So what typically happens is that between the two pipes, they put certain kind of uh, uh, certain kind of products. This is typically called a coupler. So you are joining two pipes using a coupler. There are other types of products like elbow products. Elbow is something like this. So if you join two pipes in this particular fashion, it's going to be called elbow. There is end cap, which is kind of at the end of the pipe. You want to kind of close that pipe off. There is something called a T joint. T joint is something of this sort. So there is two pipes which are at right angles to each other. This is particularly called T. So these are the different kind of products which are used to join pipes under different kind of requirements, under different contexts. Uh, so now what really happens is that there are different ways of doing these joints. The particular method that we are going to use is called electrofusion. So as the name suggests, we are going to kind of pass electricity to kind of fuse the two pipes. That's what it is all about. So within this coupler, as I said, there are going to be different filaments. These filaments can be copper. There can be other proprietary materials which are used, and then current is passed through it. And these filaments are kind of placed in a way so that the fuses kind of generates heat, and in the process, basically melts the portion out here so that both the sides are kind of joined. And then now, whether this particular welding that we do is correct or not depends on whether this particular electrofusion process has happened correctly or not. And so, based on that particular scenario, just so there are particular standards which are there, which you need to kind of maintain while doing these joints. Like I will give you an example. Sometimes what happens, the pipes are kind of placed in the ears and everything. Because of temperature changes and everything, the pipes will get disfigured. They call it ovality. Then there might be a scenario that while you're doing the joint, there is going to be grease in the region where it is, or water, or something like that. uh, there are particular processes which are supposed to be followed. Like you need to first scrape the two sides, and there is a particular number of times that you need to scrape the pipes. You'll see all of these. So these are particular standards which you need to adhere to while doing this kind of joints. Now, if you do not follow the standards, these are mainly the European standards. In India, I'm not really aware of what are the standards, but in this particular case, we were following typically the European standards. So until unless these standards are adhered to during the entire process or during the entire life cycle of electrofusion joint, uh, the resultant welding is supposed to be incorrect. What it typically means is that depending upon the particular scenario, probably the fusion is not going to be uniform, and there is probably going to be leakages or leaks or gaps in the building, as a result of which there is going to be water leakage. And what water leakage means is that there's going to be huge loss of water. And as you know, I think water is the most scarce resource that we are going to have. There is a lot of water shortage right now, and it's going to be so even in future. The situation is going to be more and more kind of intricate down the line. Uh, so I'm just kind of getting into the next one. This is a video which is in German language, so I will kind of run you through it. So this is So this is the pipe that they're going to do. They're doing. You will see them doing the measurements, and then they will basically scrape the two pipes, scrape the two sides of the pipes, put the coupler in between, and then kind of go ahead with the rest of the process. So I will kind of. So just note this is something which is called the electrofusion box. Um, this is what is called the electrofusion box. So this is actually not dumb. This is actually a smart box that has embedded Linux in it. So this is what which kind of coordinates the entire electrofusion process. What they did right now is basically there is a barcode out there which has the information of that particular pipe, the pipe dimension, the material within the pipe, and everything. So once it kind of scanned that particular barcode, that information gets inside this particular box. So this is where they started the electrofusion. So this will now continue, and then once the electrofusion process is completed, the machine will show an indicator that it has been completed. Now, as you can see, so as you can see, I think this is a big enough process and kind of invests a lot of money and everything. And normally, this particular electrofusion joints typically go for insurance, and this insurance is supposed to be for 50 years. So once you make a particular joint, and these are kind of infrastructure joints, these are supposed to last for around 50 years at the least. So now, how do you kind of go ahead, kind of giving an insurance? So there are multiple different ways that they follow. Kind of in some cases, physical pictures are taken, uh, pictures, and those pictures are given to experts, and these experts make a call whether the joint looks good or not. But if you look from outside, it's very difficult to kind of make a call what has happened inside. At times, I think they take pictures at each and every step or process of doing these electrofusion joints, and those pictures are shared. And based upon that uh, kind of visual inspection of the pictures, the insurance company makes a call whether that particular joint is going to last those 50 years or not, and then grants the insurance on that. While there are some other processes called a NDT, or non-destructive testing processes, non-destructive testing processes. What it does is it basically uses a machine which is taken to the site, and it's kind of makes use of ultrasound technologies, and there are experts who kind of run that machine and kind of use the ultrasound probe on top of the joint, and then they say based on whatever information they receive, they make an assessment. So this is based on the judgment of the expert once again. Um, and in the next slide, you will see there is a company called George Fisher. So who does that? There are other smaller companies who does kind of employ the similar kind of things, but they are not able to do it for pipes of all dimensions. But George Fisher is able to do an assessment of the quality of the well using ultrasound for almost every scenario at the site. And these are more definitive because they are able to see exactly what is happening. There are other X-ray kind of things which are done on top of the joint to kind of take a look of the interior structural construction of that well, and based upon that they make a call. These are more definitive methods. Now, this is what the problem statement is. However, what we wanted to do is that can we do something different from what the others are doing, because it's pretty much a costly process. So that's where our team, and this is something which has come up in Germany, and they started thinking around first to do data mining. So what they have done is that in the electrofusion box, EF box that you have seen, they have placed a chip, they have placed a kind of storage and chip which stores the the different electromechanical parameters, which stores different electromechanical parameters for every millisecond, electromechanical parameters for each and every millisecond. So if say the electrofusion starts for a particular pipe of particular dimension and particular construction and material at point A, and it completes at another instant B. So between these instant A and B, there would be voltage and current and resistance, and there are a couple of other parameters, electromechanical parameters, which are there. Voltage, current. These are the two main ones, and then there are other parameters as well, resistance and a couple of other technical parameters. I will not go into the detail of that because of confidentiality. So they capture the values of these particular parameters every millisecond, and that is something which is stored within this box. Now the question is, if we so this was a problem statement, and then let's see how do we approach it. So this is what we are getting. Like, we are getting the electromechanical parameters during the entire life cycle of the welding at every millisecond. So as I said, like, there are destructive physical tests which are done, and I mean, we can show you what those are, and then visual examination by experts, ultrasound, and then this is the one by done by George Fisher, who does those ultrasound testing at the location.
Lekkage, enerzijds in de drinkwaterwereld is een hot topic, maar wat geldt voor drinkwater, geldt natuurlijk ook voor de gasbedrijven. Dus ook lekkage gaat ook gepaard met kosten. Niet-destructief onderzoek kan natuurlijk ook hier bijdragen om lekkages te gaan verminderen.
En dit is eigenlijk dus een test.
So this is in German. The idea was to kind of show you, I think it's a big exercise that needs to be done on the site and everything. While our thought process was that these are the solutions available today. Can we have a better solution?
Dat gaan we doen.
So our line of research was that when we started looking at these electromechanical parameters, as I said, like here you have a kind of current, voltage, and a couple of other resistance related parameters, and this is for one electrofusion. What you see here is for this is for one electrofusion that happens. You will see when you plot those parameters on a graph during the entire life cycle of that electrofusion, you will see a pattern. And this is, say, instance 1. This is actually another electrofusion, instance 2. This is the third one, instance 3. One thing that you see in all of these, that irrespective of the dimensions and the materials, when electrofusion is done properly, I mean, so when we say properly in our case, is basically we have adhered to all the standards, and we'll see what those standards are. In that particular case, you will see that there is a pattern of these graphs, and they are same all across. So what it means that if there is a, I mean, if the jointing, electrofusion joint is done correctly under standard conditions, they all replicate a particular signature. And this signature is common to all of them. However, we see now, take a look at this. This was an electrofusion joint which was done under non-standard conditions. Or what it means is that either one or more of the standards were deviated, were not followed. So in that particular case, you will see these patterns. These are the same. These are the same parameters being put into the graph under same kind of scenario, but you will see the pattern differs. So this is actually what we call an anomaly. So from this scenario, we should be able to identify a good weld from a bad one. So if a particular welding electrofusion joint depicts a particular standard signature, we will consider that as good. And anything which is anomalous, anything which is anomalous is going to, it can be considered as a bad one. So that was the basic approach on which we started our research as such. So in this particular case, now the question is, I mean, if we have to apply machine learning to it, I mean, we needed the data. Now, where do we get this data from? So as I said, like we have this particular data mining chip which is inserted within these boxes. However, I think these boxes are kind of given to external people or external welders to kind of do those weldings, and we do not get back the result of the welding, which is basically either good or bad. So what we said was that we will simulate the data, simulate the data under laboratory conditions. And then based on the data, we'll use that data as a training set, training and validation set, and create a model. Then this model findings or this model will be applied to the real life data. And based on that, we will kind of find an assessment of whether good or bad. Now, what we wanted to do was, I mean, whenever it is good, it is supposed to be, means we wanted to give a traffic signal, traffic signal. Like if it is good, it is green. If it is bad, means when we can conclusively say that it is the welding is good, we will say it green. When it is conclusively bad, we will say it red. But there will be conditions where the model will not be able to say whether the welding, the quality of the weld with sufficient amount of assurance. In that particular case, we'll be humble enough to accept that the model is not able to conclusively give a green or a red indicator, and so it is amber. Now, what happens when it is amber? What does a customer do when it is amber? So in that particular case, he has to kind of invest into more definitive methodologies of assessing the quality of the weld, and which we showed is like uh, take ultrasound machines at the site or take X-ray machines at the site, and then kind of try to kind of assess that. And if at least in 70% of the cases we see that we are able to conclusively say good or bad, then in those good or bad cases, just means we're able to do it at a fraction of a cost. It's only the 30% remaining cases where we need to kind of expend more money. So now, I think, as we said, like we wanted to kind of simulate this data under kind of lab conditions. We cannot create, I mean, it's a huge amount of data, because we actually, when we say we simulate the data, we need to create the weldings under different conditions, which replicates the real life scenario. And then based on that data, whatever is captured, we can kind of collate that data as such. So now in for that, what we did is that we actually did a random data generator. We created a random, it's not really a data generator, it's more of, I will show you. Yeah, this is what the random data generator looks. So, I mean, so you see there are different variables. One is the welding mode, whether it will be a standard welding mode, or these are all the anomalous welding modes, or basically these are the uh, different non-standard behavior, or these are the different deviations from a standard scenario. So, like whether the pipe had not been scrapped correctly, whether they had scrapped more than kind of 3 times, whether there was lubricant in there, whether the pipe was oval, and this kind of things. So what we have done is that we have actually assigned a particular distribution to it. So 50% of the data that we generate is going to be standard, and 50% of the weldings that we do and from which we derive the data is basically going to be done under non-standard conditions. Similarly, there are pipe dimensions. There are different pipes. So we took a sales distribution of these pipes based on dimensions and applied that distribution out here. Like 35% of all the sales that is done is of pipes of dimension 63 mm. Similarly, 35% more is of pipes of 110 mm, 110 mm. And accordingly, for the rest, we have put 3 percentages. So this is another distribution. And similarly, there are different temperature scenarios. Like in certain cases, there are, and these are, as I said, this is kind of a European condition. It can be minus 10 degrees Celsius or it can be minus 45 degrees Celsius. So we have taken, what it is seen is that it's kind of a 50-50 distribution. We have taken that. So now we have actually generated the test cases out here. We have applied the simulation techniques to kind of generate these use cases, and we have you will see we have generated 500 test cases. So this 500 test cases has been generated based on the distributions which we have shown earlier. And in all practical probability, if we have done this thing correctly, then this distribution will replicate this particular distribution. So now we have 500 test cases. So that means we will make, for a particular using coupler, we will make 500 joints. So the first joint will be of pipes of dimension 63 mm, and it will be done under all standard condition, and it will be done under ambient temperature of minus 10 degrees Celsius. So for the second test case, we will do a welding once again of pipe dimension 90 mm, and the problem with that pipe will be that the pipe will be oval. As I was saying, because of if the pipes are put in the warehouses and in the outside, then sometimes it actually disfigures and it becomes oval instead of that circular cylindrical shape. So we will do that. Similarly, this is how we are going to kind of, we actually created all of these kind of weldings or electrofusion joints in the lab. And based upon that, we have kind of generated the data from there. And this is the data which is going to be our kind of the training or validation data. And in this particular case, we already know, like if it is a standard, then it is kind of, let's say 1. And if it is done under non-standard condition, it is 0. So typically what we are getting at is a supervised classification model. Supervised classification model. So based upon that, the machine will learn the signature of a successful joint, and anything which is anomalous to that signature, or any behavior, electromechanical behavior, which is anomalous to that, is something which is kind of going to be considered as a kind of a bad joint. That's what it is all about. So we generated this data. How does the data look like? I think this is one thing. Like it's not that the data will come, as I was saying, like Kaggle gives you all the data in a right format. So it's not necessarily how it happens in other cases. The data came to us in this format. So there was one. Just give me a moment. Let it open it up. So there is one set of data, and you will see the which is kind of each and every line out here is corresponding to a kind of one electrofusion joint. And these are some of the static parameters, like what is the diameter of that, what is the voltage fusion. And this is something that you had seen during the video, that whatever the scan, this is the data that they scan. And based upon this data, the timing which is needed, the time for which the electrofusion needs to happen, and all of the parameters get set in the machine. So these are more or less static parameters. So for each and every joint, or each and every electrofusion joint, we will get one record. So there are around 500 records of that, as you can see out here. So the next data that we got is something which is called the data. And that's how the name of the file was. But this is something, as you see, like each protocol ID is kind of unique to each electrofusion. So there are multiple records corresponding to that. And these multiple records are the records taken every millisecond. So you will see this protocol ID for this 2386 protocol ID. I think there are multiple records. Then for 2380, there are multiple records. So these are kind of the number of records which take corresponding to each and every instant. And then you see the biggest problem out here. Normally, in an anomaly detection model, you have a one single time series, and there is a particular behavior of the time series. If anything which is anomalous to that standard behavior, we consider it as an anomaly or a good or a bad. However, in this particular case, as you see, it's not a single one. It's kind of one, two, three, four, five, six, seven, eight different parameters. So we have eight different time series. So now, how do we? I mean, in order to kind of put a classification model, we need a single row of data corresponding to each one of the electrofusion joints. For the static data, which we saw in earlier file, we had it like that. But in this particular case, we have data for eight different time series. I mean, initially we found difficulty in kind of even understanding the structure of this data, but this is how it is. The rest of the two data is kind of relatively easier. Uh, yeah, let it open up. Yeah, one is called kind of the result data, which is the machine gives an error code 0 and 1, but that is not of much significance. And it also gives the total amount of energy which is consumed. It's called the energy total. Once again, this is kind of one record, one data point per electrofusion. You'll see 500 records out here. And then the last one is something which we have created, which is called a failure documentation, which depending of whether it has been done in the standard condition or a non-standard condition, we have put a 0 and 1. So this is the supervised part of it, where we are telling the machine whether a particular electrofusion that has been done or a particular record of data that is kind of there, whether it is correct or incorrect, whether it corresponds to a good well or a bad well. And a machine is going to kind of learn based on that. And then once it creates a model, that model can be used to infer the quality of well for any other external data. So that's where the scenario is. So at the end of the day, this is how I mean, if you put it in a JSON structure, so this is how the data looks like. So this green portion is a set of data. The data parameters are electromechanical parameters, which are static and corresponds to each electrofusion. And then there's blue ones. There are multiple of them. Each blue rectangle corresponds to one instant of a electrofusion. So as I said, like if a electrofusion happens between an instant T1 and T2, then at each millisecond, there will be this blue box created. And this blue box typically consists of the value, the snapshot value of this electromechanical parameters at that particular instant. So we will have, depending upon the dimension and the material, the duration of our electrofusion also differs. So depending upon the duration, we will get that many numbers of these blue boxes. So that's what the overall data model typically looks like. So now here where the problem is, as I said, like now we have one set of data, which are kind of static parameters, one set of data corresponding to each electromechanical parameter, I mean, each electrofusion. Then there are 8 sets of time series data. Now, what do we do about these time series data? I mean, we cannot put it in a row structure particularly. So what we did was that we used a function called TS features. We have done it in created this model in R, and there is a particular reason for that. We have, I mean, we tried it in Python as well. It did not work. We'll come to that. So we have used something called TS features. So TS features is nothing but it gives a time series features. It gives a summarized time series, summarized features or summarized characteristic of a particular time series. Then we have applied this TS feature property or TS feature function to each one of these 8 time sets. So we get 8 sets of 8 sets of 8 sets of features, and these corresponds to the time series characteristics of each one of these time series that we kind of displayed in the earlier slide. So now what we have one set of static parameters. This is corresponding to each electrofusion. And then we have 8 sets of additional features for 8 sets of time series for the 8 different time series. So now we have been able to get the data in a particular tabular kind of a structure. So corresponding to each electrofusion, now we have uh, the set of static parameters, and then the dynamic parameters or the time series has been converted into getting the characteristics of that, and that is kind of added to these. And over and above that, we add different what do you say uh, the energy total as well as the supervised or the result set where we say whether it is kind of done standard or a non-standard, and accordingly we have assigned a 0 or a 1. So I mean, so the end of it all, this is how it actually looks like. I will kind of show you that. Yeah, this is one single data row for one single electrofusion. The first sets are typically the kind of static parameters, and then corresponding to each one of the electromechanical parameters, say voltage and everything. For that particular voltage and so that for that particular voltage time series, we have got the characteristic time series characteristics. Similarly, as we go on, you will see we have got the similar characteristics for current and all other parameters. So at the end of the day, now we have the structure of the data, which is more kind of akin to whatever we get from Kaggle. And then we can kind of go ahead and apply the model on top of that. Yeah. So I mean, we went ahead and kind of, this is what you typically do. You want, means go ahead and kind of apply different kind of classifications models on top of that and kind of get the relative efficacies of that. And based upon that, you select which one is the best model that is applying to your data set. So in this particular case, what we figured out is that the boosted tree model was something which was the best suited for our kind of scenarios. And we took 2 models out of that, which was giving the best kind of efficacies. And based upon that, what we did was that we took model 1 and model 2 and applied the logic that if both the model gives an indication of good, then we kind of give a traffic light signal of green. If it is good and bad, one model gives good, the other model gives bad, or the vice versa. We are not sure about it, and hence it is amber. And if both of them gives an indication of bad, then it's a red. So this is what the traffic light signal kind of inferencing of a particular quality of the quality of a particular well is what we kind of give at the end of the exercise. So now, even in the boosted tree models, there are different algorithms which are available. We tried out each one of these algorithms and kind of figured out like what are the relative efficacies of that. And based upon that, specific to the individual product type, like we did 500 tests for coupler and created a model for that. We similarly created 500 simulated data set for NCAP. Once again, applied the models for that, created a separate model for that, and once again created one for, say, a T kind of model and a separate model for that. And then these are the based on the relative efficacies, we figured out which one are the best and selected 2 models for each one of them. And depending upon the logic which I showed you in the earlier thing, we went ahead and kind of created a inferencing as such. So now I think uh, it is important that you create a model, but this model needs to be applied to a particular scenario. So what we have done is that we have exposed this model as a service, and I'm just kind of running this video for you to kind of show you what we did for this. Since this is in a separate machine, I had to kind of create a video out of that.
Hi everyone, we have already seen how we have kind of defined the supervised classification machine learning model to predict the quality of well being done through electrofusion. So in this particular case, what we have additionally done is exposing that particular model as a service. So this is how we are using Postman to make a call to that service, and what we pass as an input to that service is the same data model which we have seen earlier. The first part of the data model is the JSON input that we kind of use in order to make a call to that uh, service. So the first part is typically the static parameters as we had seen earlier, and then subsequently these are uh, the continuous information about the different parameters like voltage and current taken during every instant of our electrofusion life cycle. And that is what we are passing. And then if we make a call to that API, we will, as a response, get a traffic signal, which is either green or red or amber. Green signifies that the weld has been perfectly fine. In case of red, that means the weld is definitely incorrect. While there might be certain cases where we get an amber response, which would mean that the AI is not capable or uh, AI is not able to predict the quality of the weld.
So now I think as you say, like we kind of expose it as a web service. Now, where is that web service going to be used? Or basically, we expose it as a service. It can be consumed by any application, any line of business application. However, we were making it work into something called a workflow app. So we have created a workflow app. This is currently in Germany. It is going to be kind of launched globally. So this is the electrofusion box that is shown out here. So this particular workflow app actually helps a plumber or a contractor or the hierarchy of operations above and below them to kind of track and monitor these kind of electrofusion joints through a mobile. The mobile app is kind of connected to this electrofusion box over Bluetooth, and that's how it kind of gets the data out of that electrofusion box and accordingly goes ahead and kind of coordinates the entire process. So the idea is to actually once the electrofusion completes, we will take the yeah, just take a look at this. So this is what we have done. Like the idea is to like once the electrofusion completes, as you know, this electrofusion box has the data. Electrofusion box EF box has the data. So that data is something that we are going to take into the workflow app, and that workflow app is going to make a call as to to the AI as a service to the AI model, and that model is going to kind of pass a inference, which is whether the weld quality, and that weld quality is kind of either red, green, or amber. So this is the approach at the end of the day. So I think with that I will kind of end my presentation. I'm open to kind of any kind of questions you have. And by the way, I think these are my coordinates. If you want to kind of get connected to me with your suggestions, questions, or anything, just just let me know about that. So, Deepak, are there any questions? Okay, then. Thanks, everyone. I think have a great weekend. Bye bye.